Good afternoon, everyone. Today's lecture number 13 of this heat treatment class, and today's topic is on annealing and normalizing heat treatment. This annealing and normalizing heat treatment are one of the important heat treatment which follow in industries. Basically, normalizing is one of the important heat treatment which is given to steels in industry. And if you people have seen that this one, predetermined temperature and soaking temperature for annealing and normalizing is this one. So we can have various kind of annealing heat treatment, but full annealing is one of them, which we'll discuss right now. So full annealing heat treatment. So if you have remember the heat treatment cycle, we have basically 3 heat treatment cycles, right? The first is heating cycle, if you remember, and the second one is the holding, or that is soaking cycle, and finally we have a cooling cycle, right? So here you understand, in full annealing heat treatment, the edge received steel is taken to the austenitizing temperature, right? And if you people remember, the austenitizing temperature is not fixed, basically for hypoeutectoid steel or hypereutectoid steel, because if there is a change in composition, the austenitizing temperature will change, right? Then after taking the steel to the austenitizing temperature, we have to hold the steel for a particular duration of time. And if you remember, that depends upon the composition of steel again, it depends upon the thickness of steel, composition of steels, and like that, right? So after doing soaking, then finally we have to do cooling. And this part is important. In full annealing, the cooling will be done inside the furnace. What it means? It means you'll take the steel sample first, then we put inside the furnace, then we switch on the furnace, and the furnace will take the steel to austenitizing temperature, and it has to be hold for a certain duration of time. After that, what we'll do, we'll switch off the furnace. That's all. We are not going to take out the sample, right? The sample will be still there inside the furnace, and we'll switch off the furnace. We'll allow sufficient time to make the sample cool. So now there is an interesting table here. You can see this is steel composition, and here we have predetermined temperature and soaking temperature and cooling rate. So for hypoeutectoid steel, you can see the predetermined temperature and soaking temperature for this full annealing heat treatment is A3 temperature plus 50 degrees centigrade, right? That means we have to take the sample 50 degree above A3. And A3, you remember, it is upper critical temperature. To go into full austenitic resin, there will be full austenitization will be there. Then after what? Then cooling rate is very slow cooling rate, that is furnace cooling. But when we have a eutectoid steel, which is 0.88% of carbon, here we have to take the steel above A1. Basically, you can say above A1 means A1 plus 50 degree or 40 degree, like that, to make it full austenitic resin. Then finally furnace cooling will be done. And if we have a hypereutectoid steel, the composition of steel is above 0.88%, then this one is important. You have to remember this one. In between A1 and ACM. So basically you can say we have to heat the steel above A1, but the temperature should not go above ACM. This kind you can call this one as partial annealing. Partial annealing, right? This one is full annealing, this one is full annealing, but this one is partial, right? Because the entire initial structure will be not become austenite. So I have written not fully austenitic resin here. And finally Same furnace cooling will be done. Now, yeah, there is an interesting line here. For alloy steels which contain strong carbide forming elements, predetermined temperature and soaking temperature is high compared to plain carbon steel. So if we are dealing with a alloy steels, high alloy steels, or steel containing certain amount of alloying elements, specific alloying elements, in that condition we can go for a high temperature like 70 degree, 80 degree above, or we can go for um, A3 plus 100 degree or 150 degree. It depends. It depends. So I have a question here. Which kind of alloying element if will be there in the steel? We have to go to a very high temperature compared to that of a plain carbon steel. Can you give some example? Do you have any idea? I think I this one I have told you while we were discussing about the variables of heat treatment, different variables.
Sir, vanadium, niobium.
Yes, yes, very good. Vanadium and niobium. Excellent. So basically, vanadium and niobium they form very strong carbide, and the melting point is above 1000 degree, above 1050 nearly. I don't exactly remember, but as I remember, it is above 1050 degrees centigrade melting point, right? So all we want, this carbide should get dissolved into the austenite matrix. We our our priority is to form a homogeneous austenite phase. To make the austenite homogeneous, we need to dissolve these carbides, the strong carbides like vanadium, titanium, niobium carbides, right? So unless until you go to a very high temperature, it will not dissolve. Okay, do you people remember at 850 degrees centigrade which carbide will get dissolved in the steels, or above like 750, 850 nearly? Which kind of carbide get dissolved?
Cemented.
Cementite, yes, very good. Cementite is easily dissolved into the austenite phase. But if you have vanadium carbide, niobium carbide, titanium carbide, some alloying carbides, they are very difficult to dissolve. They need a very high temperature, right? And okay, so this one is very important. Another point is sometimes we need also more soaking time. Do you people remember why we need more soaking time?
It's a complete diffusion ପାଇଁ.
Yes, yes, very good. See, one part is the dissolution. Suppose a carbide is present at the center, for example, of the grain. It will get dissolved at a particular temperature. The temperature will take care of that dissolution part. But what about the diffusion part? We need a homogeneous austenite phase. Homogeneous austenite phase means you go to any part of the grain, everywhere the alloying element concentration, the carbon concentration should be same. There should not be any segregation kind of thing, right? So diffusion has to happen there, which is a time dependent phenomenon. Temperature as well time, right? So what happens? So since these elements are heavy elements, the diffusivity is very low. So we have to hold for a long duration of time for that. And very good. Yeah. Uh, and I think this question is asked many times. Why for hyper-eutectoid steel, that means the steel which contains more than 0.88% of carbon, why we are not going above ACM? Because above ACM, we have a complete austenite phase. But we are, rather than we are going in between this A1 and ACM. This is a very good question. Why we are not going there, going in that condition? This is completely related to the cooling rate. Completely related to the cool. The answer is lying behind the cooling rate. You can see the cooling rate is furnace cooling. That means it is very slow rate of cooling. Can anybody remember what is if a cooling rate is very slow, Then what is the other name of that? In the phase diagram, we use that name.
Equilibrium cooling.
Equilibrium cooling.
Yes, equilibrium cooling. Very good. So the answer is what? The first point is prevent grain coarsening. Let me justify this one. I have, okay, yeah, this one. Just look at this one. This is a CM line, right? Basically, we want a homogeneous austenite in annealing process. But if it is hyper-eutectoid, suppose from here to here, we are going like this and we are going 50 degree above this temperature, A3. But if we have a hyper-eutectoid, still this one, hyper, we are not going above this one, like here or here. We are going in between this, just above A1, 50 degrees centigrade above A1, for example, here in this region. So this is a partial annealing kind of thing, not complete annealing, right? Because here we have two phase region, gamma and FE3C, right? This is because you can see this one. Sorry, you can see this one. Furnace cooling, very slow rate of cooling. Very slow rate of cooling means the cooling rate is so slow that precipitation of cementite will be there along the grain boundary, and that precipitate will grow along the grain boundaries completely. So entire prior austenitic grain boundary will be covered by this cementite precipitate, right? That is the main issue actually. Fine. That basically depend upon the slow cooling. Slow cooling means we are giving a lot of time for the precipitation to be happening on the grain boundaries, and this and growing of the cementite networks. Yes. So cooling, since the cooling rate is very slow, enough time is there for the precipitation and growth of the precipitate. Which precipitate I'm talking about? It is cementite. So cementite is getting precipitated along the grain boundaries, and it is growing along the entire grain boundaries. All the prior austenitic grain boundary is full of cementite, and this is called a network of cementite. Cementite network will be there. Can anybody remember what happens if we have a network of cementite in a structure? What is the main issue?
It's
It will
brittle.
get brittle.
It is a brittle phase. Then what will happen? Cementite is obviously a brittle phase, but what will happen if there is a network of cementite?
The dislocations may easily travel.
Dislocation may
The
easily
crack,
transfer. What
crack
you are
may
saying?
propagate along the grain boundary.
Very good. Sivasis is right. The crack, if basically crack always initiate in a weaker region, the portion which is weaker. So cementite is a brittle phase. That is a weak portion. It cannot withstand the load. So crack will initiate along the grain boundaries, and since it is a network, complete network is there, crack will easily find a easy way to propagate along the grain boundaries. The material will get failed, right? Cementite is this is the main answer to this question. And what are the other reasons? Other reason is, you can see this is clearly visible. SCM line is going up. SCM line is going up. Suppose I will take this much of composition of steel, right? So that means I have to go to a very high temperature for complete austenitization, right? Because the line is moving up. So that means more is the concentration of carbon, more I have to go to a very high temperature. If you are taking the steel to a very high temperature, what happens basically to the grains? What happens to the grains? At a very high temperature, what happens to the grains?
Grain become coarser.
Grain become coarser. Very good. So which grain will become coarser here? Which grain will become coarser in this area?
Austenite.
Yes, we will be having a coarser austenitic grains. And you understand, after making the grain coarser, and then we are cooling it to room temperature again. So finally, what will happen to the structure at the room temperature?
A coarser grain inside product.
Yes, the product grain will also become coarser. Two things are there. One is slow cooling is there, enough time is there for the grain to coarsen, and the part is initial grain is also bigger. You people are getting my point? If initial grain size of the austenite is coarser, then final microstructure will be also coarser. So if we have a perlite, then it will be a coarse perlite. Fine. And sometimes another problem can be arise, that is decarburization may occur. See, since the temperature is very high, because temperature is increasing with the percentages of carbon. So if you're going to a very high temperature, decarburization may occur. Decarburization means removal of carbon from the surface basically. And you understand, carbon is one of the major alloying element which enhance the hardness and strength of the steel, right? So if carbon will get removed from the surface, the surface will become weaker. The wear resistance will decrease, the hardness will decrease on the surface, right? This is the another problem we have. Oh, okay, how you people have understood why for hypereuctectoid steel we are not going above SCM. We are just remaining over here. This is our predetermined temperature in this region. You people can write down in your examination paper, right?
Yes, sir.
Okay, very good. So finally, what I can conclude is we will be having what? Poor mechanical properties. In simple, what I can write? Poor mechanical properties. Poor mechanical property will obtain steel if it is heated above SCM. Okay. So you people have understood what is full annealing exactly, right? Then we'll discuss this one. Yes, we can classify this annealing into few category. That means, if you remember, we have many kinds of annealing process, right? If you remember, we have many kinds of annealing. One is this full annealing, one is periodizing annealing, one is recrystallization annealing, one is stress relieving annealing, right? We have many annealing processes. So what we have discussed, this one is full annealing. Now we can also classify the annealing on the basis of predetermined temperature and soaking temperature, right? So one is called full annealing, one is partial annealing, partial annealing, one is subcritical annealing. That can be explained with the help of this temperature versus time curve. This is a heat treatment curve, right? Temperature versus time. You can see you can see this line. This is A1. A1 is what? Lower critical temperature. And this is your A3, that is upper critical temperature. So subcritical annealing means the annealing is done below the A1. That means our predetermined temperature and soaking temperature is below A1, right? And what about partial annealing? Partial annealing, you can see the predetermined temperature and soaking temperature is in between A1 and A3. That's why it is partial. In between lower critical and upper critical temperature. And what about full annealing, which already we have discussed? That is basically predetermined temperature and soaking temperature is above A3 or above upper critical temperature. I think you people have understood now, right? So can you people tell me, in between this one, and this one, where phase transformation will be there, where there will be no phase transformation?
In
In
full and
full
partial,
annealing,
there
there
will
will
be
be phase transformation.
phase transformation.
In full and
And
partial, we have phase transformation. Very good. And in subcritical?
we don't have any phase transformation below lower critical temperature.
Yes, we do. Very good. So here you can understand critical temperature. If you remember, critical temperature and temperature at which phase transformation will happen, a start. These are two phase transformation temperature or critical temperature, A1, A3. But in subcritical annealing, we are not hitting the steel above A1. We are hitting the steel below A1, right? Or near to the A1, not exactly above A1 or exactly A1. So there will be no phase transformation involved in this subcritical heat treatment, right? So now the question is, why then, what is the need of doing subcritical annealing? The need of doing subcritical annealing is basically subcritical annealing is also a high temperature, not very high, but still it is a high temperature where these things are happening. Thermal activated phenomena are happening. Thermal activated phenomena are happening, right? So thermal activated phenomena means the phenomenon which is activated at high temperature, basically. What are those? The recovery, recrystallization, grain growth, and carbide agglomeration. Can anybody tell me what is carbide agglomeration? What is the meaning of that? Just use your mind. Carbide agglomeration.
Precipitation of carbides.
No. Precipitation is different thing.
Uh,
Agglomeration
for,
is different thing.
sir, formation
Yes.
of bigger size carbides from small size carbides.
Yeah, you can say like that. Basically means the same thing which you told. Small carbides become bigger carbides, but they will take a shape of spheroid, spherical shape. Okay, with this one I have written over here. So finally, you understand what is the main motive of doing subcritical annealing. You understand, if you do recovery, recrystallization, grain growth, and carbide agglomeration, then the steel will become harder or softer. If recovery, recrystallization, grain growth will be happening in a steel, then it will become soft or hard.
Soft.
Hard.
Somehow, how it will become hard?
So soft.
Now let Soumya or Ranjan to explain how it will become hard. Soumya, can you explain how the steel become hard if recovery, recrystallization, grain growth will happen?
Sir, carbide percentage is more na.
Carbide percentage is more. Are we adding any kind
Sorry,
of
sir. Sorry, sir. Soft, sir.
how it will become soft?
Sir, we are not adding any carbide. So carbide is fixed. Then recovery, recrystallization, then both are soft.
Okay, how on recovery, recrystallization, grain growth the metal becomes soft? Okay, how many of you can explain how a recovery, recrystallization, and grain growth brings softness in a material?
So
How many of you
ductility
can?
increases.
Sir,
Shiva?
during recrystallization.
Strain-free material develops.
Very good. Strain-free materials get developed. So what is the meaning of strain-free materials get developed?
Sir, it means it is ductile, so it's because softens the material.
Why the material becomes strain? What is the meaning of strained material?
So strain means there is a lot of dislocations in that.
Very good, very good. That means we have lot of dislocations in the materials. We have lot of stored energy in our materials, right? So we will remove those defects, dislocations. Strain hardening effect is getting removed. In recovery, lot of dislocation will get annihilated. In recrystallization, rest of the dislocation will get annihilated, and the grain become strain free, right? And finally, also grain growth is there. The grain become coarser. So finally, dislocation cannot easily move. So that's why it is becoming softer and softer, right? An agglomeration of carbide. Okay, how if carbide become agglomerated or cemented become spherical, how it brings softness in a material? Let me see how many of you can explain. If cemented will become spherical or agglomerated form, how it brings softness in a material?
Sir, the surface area of carbides can minimize by the spherical shape.
So
So hindrance to dislocation, or it may produce some less obstacle to dislocations motion.
okay. And what about brittleness property? If carbide become agglomerated, the brittleness property will decrease or increase, or there will be no change in brittleness property?
So brittleness property increases.
Brittleness property increases. What about others? Let me see. If you have a needle shape carbides, and in another case you have a spherical carbides, which one will be having more ductility and which one will be having more brittleness?
Needle shape more brittleness, spherical
Yes,
ductile.
yes, very good. Why? Can you justify that?
Strength, strength concentration or stress
Yes, not
concentration.
stress concentration. When you are
Stress
applying
con.
load on the material, the load should be uniformly distributed everywhere, right? But the problem is what? At particular edge of the needles or at the corner of the needles shape carbides, the concentration of stress is high. That is a stress riser. And once there is a stress riser, crack will initiate from there only. That is the crack initiation site. So now, can you people tell me again, if carbide agglomerates will be there, a spherical form of carbides will be there, like cementite, spherical form of cementite, it will be ductile or it will be brittle?
Ductile.
Yes, the answer is ductile. Okay, anyways, you people have understood this subcritical, partial, and full. Okay, I have one line here. Full and partial annealing involves phase transformation, right? But subcritical annealing do not involve phase transformation, any kind of phase transformation. Now, we'll discuss another heat treatment that is called normalizing heat treatment. Normalizing. Everything will become normal kind of thing. Normalizing. So here what we will do, we take the edge receipt sample. So edge receipt steel to austenitic temperature. After taking the steel to the austenitizing region, then we do soaking. We have to hold the steel for a certain duration of time. And finally, this is important part. We are doing cooling somewhat faster as compared to that of the annealing process. We are cooling the sample in air. That means what we'll do, we have a steel sample, we will insert the steel sample into the furnace, right? Then we'll switch on the furnace. Then the furnace temperature will take the steel to the austenitizing temperature. Then after reaching the austenitizing temperature, we have to hold the sample for a particular duration of time that depend upon the thickness of the material or alloy compositions, right? Then finally, when soaking time is over, we have to take out the sample from the furnace and put it into the air, normal atmosphere. So that is called normalizing, cooling in air. But earlier one is annealing, where full annealing, where we are doing furnace cooling, cooling inside the furnace itself. But here we are taking out the sample from the furnace and cool it in the air, right? So cooling rate is higher somewhat, right? Now this is showing steel composition, predetermined temperature and soaking temperature, cooling rate. So if we have a hypoeutectoid steel, steel is the composition of steel below 0.8 weight percentage. Here what is happening, you can see we are going 50 degrees centigrade above A3, same upper critical temperature, 53 degrees centigrade above upper critical temperature, and to do full austenitic region. Finally, we are doing air cooling. Same for eutectoid steel, it is above A1. Suppose 50 degrees centigrade above A1, lower critical temperature, full austenitic region and air cooling finally. If we have a hypereutectoid steel, and this is very interesting, you can see we have a hypereutectoid steel, we are going above ACM for full austenitic regions, then air cooling. So now I have a question. Can you people think of this in full annealing heat treatment? In hypereutectoid steel, we are not going above SCM. Suppose, let me show you. We are not going above SCM when we are doing full annealing. But when we are doing normalizing, we are going above SCM. Why? This might be a question. Can anybody think of this?
So because of
Sir,
cooling
in
rate,
normalizing, cooling rate is higher.
Cooling rate is very high, yes? Or very low?
high.
Very high.
High. So what will happen?
Grain coarsening will not occur.
Grain coarsening will not occur. I told the grain coarsening depend upon the initial austenitic grain size. If initial austenitic grain size is already coarse one, the final product will be also having coarser structure. That is one part. But listen my question. I am talking about only hypereutectoid steel. In full annealing heat treatment for hypereutectoid steel,
The
from this reason to
cementite
this reason, we are not going
precipitate
above
will not be
SCM.
there.
But in case of cementite will be not there.
So precipitate coarsening that.
Precipitate coarsening will be not there. What you are saying?
So we are
Hmm.
doing fast cooling, so it will not get time for coarsening of precipitates, cementite precipitates.
Coarsening or to spread along the grain boundaries?
Mm,
Network like precipitation will not occur.
Not there. Very good. Very good. We can have a precipitation, obviously, because it is a hypereutectoid steel. So where the pro-eutected cemented phase will be there. Pro-eutected cemented phase will be there itself. You cannot avoid pro-eutected cementite unless until you are going for non-equilibrium cooling, right? So cementite will be there and precipitate will be there, but it will not spread along the grain boundaries like in earlier stage. Why? The answer is due to very fast rate of cooling. Time is not there. Enough time is not there to spreading of this cementite along the grain boundaries and forming a network-like structure. This network-like structure is dangerous. But if the cementite is discontinuous, you got my point? If a cementite is discontinuous, so that is fine. There is no problem. But if it is a continuous structure, once a crack will initiate, it will easily propagate. But if it is a discontinuous kind of thing, so if crack will initiate, it will stop. It cannot easily propagate. So that's why. Already it is written over here. You can see since the cooling rate is fast enough, shorter time is available, then annealing, it prevents the formation of network of carbides along the prior austenitic grain boundary. I think you people have understood.
so does it affect the decarburization?
Yes, it might affect. It depends upon the temperature itself. Suppose you are going this much of temperature here, so obviously few amount of carbon will get removed from the surface of the steel. But if you are going like here only, just above here this temperature, this is fine, no problem. But if you're going to this temperature, then it is a problem. It depends upon temperature again. How high you are going to the austenitizing region, how high you are going, right? But if you're nearer to the SEM, that is fine, no problem. So our priority is to have cementite in a discontinuous way, or in a spheroidal form or spherical form. That is good. So always you have to remember, since cementite is a very hard and brittle phase, it is basically a weak portion of the steel. It is a weaker region. Crack always initiates from there. But if the cementite will be in spherical form, that is good. But there should be a uniform distribution of spherical cementite, right? That is one part. Another part is, if cementite is only present along the grain boundaries, that should be discontinuous one. It should not be a continuous network. That should be discontinuous one. That is also fine. Now we have no problem much. So the best one is spherical form of cementite is good, very good. It will provide you good toughness and ductility also, right? But if there is a heterogeneous nucleation only, a distribution of cementite is not uniform, then discontinuous cementite is good. But it should not be, again, needle shape or completely irregular shape. That is also detrimental, because crack initiation points are there. Or it may behave as a crack or stress riser, right? Okay, so now I'll show you a very beautiful image here. Just look at this one. This is temperature versus time. Sorry, this is temperature versus composition, which will show you different temperature range. That is temperature range for different annealing and normalizing process. You can see normalizing temperature is this one. This one is the normalizing temperature, upper part. And annealing temperature, for full annealing temperature, is this one, just below the normalizing. You understand, this is your A3 upper critical temperature for hypoelectric steel. And for hyperelectric steel, this is the upper critical temperature. And this is the lower critical temperature, or that is A1. So if you compare spheroidizing, and so you can see spheroidizing annealing temperature just below the A1. So
So what is periodizing?
spheroidizing means we have to convert our cementite networks into spheroids or spherical particles. The cementite carbides will take the shape of spheres. It may not be exactly sphere, but still it is spherical shape. Now you understand?
Yes,
Now
sir.
you got the answer, yes. So now from this image, can anybody tell me in which case complete homogenization happens at low holding time? In which case there will be a complete homogeneous structure will form at a low temperature. Sorry, at a less interval of time.
Normalizing.
Normalizing, very good, because the temperature is very high. Very good. And this one also shows you in spheroidizing there is no phase transformation. Only the shape of the carbides, which is the shape of the cementite, is becoming spherical, right? So there is no phase transformation here. Phase transformation will happen in normalizing and in full annealing. But here you can understand for hyperelectric steel, if you remember, carbon percentage above 0.8. So full annealing temperature is in between A1 and A3. Sorry, and in between A1 and ACM here. So this is a partial annealing kind of thing, right? Which we already have discussed, full, partial, and subcritical. So now can you people tell me, if you have this kind of picture, can you people tell me which one is full annealing, which one is full annealing, which one is partial annealing, which one is your subcritical annealing?
Yes, sir.
Can you people tell me?
Sir,
You have to justify that.
full annealing is above A3,
Yes, very good.
and that spheroidizing part is subcritical annealing,
Very good.
and partial annealing is in between A1 and A3. That is uh,
That is,
that gray portion.
yes, yeah, that is
Yeah,
for. Hmm.
that partial annealing, but below A3.
Hmm. So, so this full annealing will be done for which kind of steel?
Hyper.
Yes, very good. Hyper. Why? Why for hyper steel? For full annealing of an hyper steel is done in between this temperature. Why? Just
So
few minutes
because
before we
the
have
Because
discussed.
slow rate of cooling.
heat radiation and cooling rate, all that things.
A few minutes before we have
Scientific
discussed all those things.
Precipitations, cementite precipitates, coarsening.
One point is the grain become coarser. You can see the temperature is rising. If you are going above SCM, temperature is very, very high. Right? So austenite grains become coarser. So final product also become coarser. Coarser grain material is having a poor mechanical property. The strength will be less, hardness will be less. Right? Another point is what? If you're going above a very high temperature, then you are cooling it very slowly because it is annealing, furnace cooling. The time is so high that the cooling rate is so slow, or the time taken for cooling is so high, the cementite will get precipitated along the grain boundaries and it will entirely spread along the grain boundaries. It is forming a network structure of cementite, which brings brittleness into the materials. And if there will be a crack initiation, it will easily propagate along the network structure. Finally, the metal will fail. You people have understood now again? Okay. So now I will discuss objective of annealing and normalizing. So first objective you can see improves ductility, improves formability, right? So since can anybody tell me why ductility or formability will be high when we are doing annealing?
Because here cooling rate is slow for furnace
Very good.
cooling.
So what? Yes.
So diffusion, we are giving that much time for diffusion.
Yes. So finally,
So we have our product grains coarser.
very good, very good. Since the product microstructures are coarser, right? That's why it has more ductility and improved formability, right? You can easily deform it to give any shape, right? And second one is you can see remove internal stresses completely. If there is any internal stresses which may be developed due to maybe machining, uh, which develops due to which has PVLOPT during machining, welding, cutting kind of thing, solidification also, solidification. All the internal stresses developed during these things will get removed. There will be no internal stresses. Okay. And finally, you can see decreased electrical resistance. That means electrical property increases and there is an increase in the magnetic property also. So these are some objectives of annealing process. So that's why you can call a annealed steel is more ductile, less harder, less stronger, less tougher. It has good electrical property, good magnetic property, and very low internal stresses are there, right? So similarly, normalizing. What is the objective of normalizing? To improve hardness and strength. Can anybody tell me why hardness and strength will improve in normalizing? Tell me quickly. Why hardness and strength?
Fast cooling rate.
Very good. Due to faster cooling rate. Then
We don't have that much time for diffusion, so product grains are finer.
finer.
That's why
Very good.
our hardness and strength is more.
So you understand, in normalizing we are doing air cooling. Air cooling means it is a very fast rate of cooling. So grain are not becoming coarser. They remain finer grain. So finer grain have high strength. And you understand why finer grain material have high strength. So one of the main purpose is to grain refinement of rolled and forged steel, which causes coarser grain. If you want to refine the grain size of the rolled and forged steel, you can do normalizing, which is done in industry basically. And it also improves machinability of the steel. Machinability means how easily it can be machined, how easily it can be cut or given some deformation somewhat. But there is a limitation to the annealing process, you have to remember. Annealing process is a prolonged heat treatment cycle. So if a heat treatment cycle is prolonged, it is time consuming and temperature is also very high, then it is a quite expensive process. So normalizing is preferred treatment in industry rather than annealing. You have to remember this one. The microstructure difference and property difference in annealed and normalized steel. See, this question and this question is asked a lot of time to the students during interview. So what is the difference? They might ask like, what is the difference between annealing and normalizing? Or they may ask him to differentiate the properties of an annealed steel and a normalized steel. So you can easily differentiate them. The first difference you can see what? Coarser microstructure. What is the answer? Why? Due to what I will write?
Slow cooling.
Slow cooling. Very good. Cooling rate is slow, or furnace cooling. So if you have a ferrite and pearlite, so you have a coarser ferrite and coarser pearlite. Right? Similarly, if we have a pearlitic microstructure, so what will happen to the interlaminar spacing here?
It will be more.
Yes, more interlaminar spacing. Very good. How many of you remember if interlaminar spacing is more, what happened to the strength and hardness?
Strength decreases.
It may decrease.
May decrease. What is may
Will
decrease?
decrease.
It will
Yes.
decrease.
So I should not write. You can understand that strength will decrease, the hardness will decrease. Then what is the strength of the steel we have? Low or high?
Low.
Low. Very good. What about ductility?
High.
High. Very good. Coarser grain. Toughness?
Low.
Very good. Low. Because it is more ductile, that's why. Ductility is so high that the toughness decreases. Similarly, interesting point is there, improve machinability of medium carbon steel. You understand, medium carbon steel means the carbon percentage is very high. So high carbon percentage make the steel harder and stronger. The strength is high, it is more harder. So if you do annealing on that steel, you can improve the machinability, right? Because it brings ductility. Already it is having high hardness and it is bringing ductility. So toughness will be good and you can machine it well, no problem. Similarly, normalized steel. So normalized steel have finer compared to the annealed steel due to what I will write, due to
Fast cooling.
Fast cooling.
Faster rate of
fast
cooling.
cooling. Fast cooling rate compared to annealing. Then if pearlitic microstructure, what about the interlaminar spacing?
Less.
Yeah. Less. Very good. So what happened to the strength?
High.
High. Very good. Comparison to annealing. You're right.
Annealing.
Ductility?
Less.
Low. Toughness?
High.
High.
High. High or good you can write. Good. then it improves the machinability of low carbon steels. You understand, low carbon steel is already carbon percentage is very low. It is already ductile, low hardness, low strength. But if you are doing normalizing, we are refining the grain size. So grain size refining will gives to strength. So it has good machinability.
Hello, sir.
Yes. You have any question?
Sir, how machinability is related to strength? I mean, for
Machinability, see. Okay, anyways, you should understand. Suppose I will give you a plate of steel. I want to cut it, for example, with a tool, right? But the moment I am cutting, if it is a ductile one, somewhat, it is a ductile one. What will happen? Cutting will be easy or difficult if it
Easily,
is ductile. If it is ductile, it
easy
can be cut easily. How you are saying?
or
Ductility
difficult?
means it will deform. It will deform, no? You want to cut it, but the material will try to deform rather than cut in a sharp way. So what will happen? The tool will get stick to the material due to deformation. Sticking of the tool will take place. But if a material is harder one, somewhat tougher one, you can easily cut it. It will give you a sharp edges to cut it. But if it is a ductile one, high
Sir,
ductility,
if
yes.
the material is very hard, then it damages the parts of the machines.
Sorry, can you repeat?
Sir, if the material is very hard, it will damage the parts
Hmm.
of the machine.
I am not talking about very high hardness. Just look at this one. Low carbon steel is ductile, but you are doing normalizing. So normalizing will give you which kind of structure? Fine, fine grain. Fine grain structure will give you more toughness and good strength. Yes, but already ductility is there. So combination of them will be what? A tougher material? Yes or no?
Yes, sir.
This one is ductile,
Yes,
but
sir.
you are doing normalizing. So it try to increase the strength due to refining the grain size. And grain size refinement gives you more toughness value. But it is a ductile. So resulting thing will be tougher one. You can easily machine it easily, no problem. But if you do directly cutting or you do some cutting action or machining action directly to the low carbon steel, then what will happen? It is a ductile material. The tool will get stick to the machine. The tool will get stick to the sample while cutting. Cutting will be not easy. It will get deformed during the cutting action. Right? So that is the problem. So I will end the topic here. So you have to remember this one. There is many people ask this kind of questions. What is the difference between annealing and normalizing? So can you people conclude this one? What is the difference between annealing and normalizing? Full annealing, basically. I'm not talking about only annealing. I'm talking about full annealing and normalizing. Let me see how many of you can tell me. What is the difference between annealing, heat treatment, and normalizing? How you can differentiate?
So full annealing is done above upper critical temperature. Sorry, below upper critical temperature and above lower critical temperature. But normalizing is done above upper critical temperature. And the
Is
cooling
this
rate,
a difference? But you are telling the difference on the basis of weight percentage of carbon. But I am asking in a general way. Just tell me what is the difference between full annealing and normalizing. That's all. How you can differentiate them?
cooling rate is
First, you can simply say cooling rate. Cooling rate is
slower.
can you people wait? Yes, I'm back. So the cooling rate here is what? Slow. Here cooling rate is fast.
Comparatively fast.
I'm comparing, so I can write fast directly. Slow means what I should write here? Which kind of cooling?
Equilibrium or furnace cooling.
Furnace. Yes.
Furnace.
Very good. So here what should I write?
Air cooling.
Air cooling. Very good. This is one of the best difference we have right now. Second one is if you are talking about the temperature, predetermined temperature. Predetermined temperature is somewhat high. Yes or no? You have seen the plot here? This one.
Yes, sir. Yes, sir.
So high predetermined temperature, here low predetermined temperature. Sorry. Low. We are comparing here, so you should not be get confused here, right? Any other difference? Can you tell me?
Coarser product and finer product.
Yes, coarser, coarse microstructure. You should tell microstructure better, huh? Product is not a good term. And here we have fine. Anything else?
Sir, annealing is a costlier process, expensive one.
Sorry, annealing is? Can you repeat?
Expensive one.
Expensive.
Sir, is an expensive.
Yes, expensive process. Why it is expensive process? You understand. A lot of temperature is involved as well as more time interval it is taking. It is less expensive. So that's why in industry we prefer to do normalizing. Anything else? You can also write high strength, high hardness of steel. Here, what I should write? High ductility.
Sir, in
Sir,
annealing,
high
we are
strength
getting
annealing
high
and
ductility.
Sorry. Yes. Here it is. High strength and high hardness of the steel. Here it is. High ductility and low hardness and strength. So these are the main differences we have. Okay. So I'll end the topic here.